My name's Jeff. So I'm going to talk about, a subject which has a lot of opinions, and hopefully maybe present some information that some of you have not heard about before. So if I were to ask the question, this is a rhetorical question, what was the first electronic digital computer?
ENIAC.
Oh, go ahead, shout it out. We have ENIAC.
Z3.
Before we go forward, can you define what you mean by a computer? Does it have to have a stored program?
No, we're not doing Turing complete, stored program. When people were creating these things in the 30s and 40s, that wasn't a consideration. They were trying to create a device that computed numbers.
A device is computed.
Does electronic include electromechanical?
No.
That would be Pascal's crank-o-matic.
Yes, that would have been digital, but it was not electronic.
Depending on what you're defining it.
Right.
So it's kind of hard.
So it was a trick question. So the thing was, ENIAC was electronic. It actually is related to the subject at hand. UNIVAC was later. Colossus was at a similar time frame in the UK. The Zeus Z1 to Z3 were electromechanical. He did flirt with vacuum tubes shortly, but under the conditions he was building his computer in, it was amazing he got done what he got done. Trying to build a computer out of scrap and mostly handmade parts that he could get a hold of during the war.
He invented floating point.
Yes, well, we used floating point, basically. But yeah, he actually made a floating point in his relay-based computer.
You are right.
That I would believe.
I would
Okay.
say university.
So some of you obviously have heard of Atanasoff, and some have not. The computer was, after the fact, named the ABC computer, which he did as a nod to the graduate student that was his main helper and co-inventor. So this is John Vincent Atanasoff. He got a Bachelor of Science in Electrical Engineering from the University of Florida because at the time that was the most theoretical course they offered. He really wanted to be a theoretical physicist. And then in 26, he got a master's from Iowa State College, which is now Iowa State University, and then got his PhD from the University of Wisconsin, and he went back to teach at Iowa State College, being the only theoretical physicist on campus, and he also taught mathematics.
Question. His father had a slide rule back at the beginning of the last century. Not many people had slide rules or even knew what they were or how to use them. So,
Right.
What was his father?
His father was a Bulgarian immigrated here at age 13 with an uncle. His uncle left at 15, and his father managed to put himself through high school and got into college and became an electrical engineer. So at this time when he taught himself, Atanasoff taught himself to use the slide rule. His father was the engineer at a phosphate mine in Florida, which, being in Florida, lightning strikes, electrical motors, that was a lot of the work. And his mother was a school teacher, and as he learned about mathematics, they didn't have a school set up in this area yet, so he was learning on his own, and his mother taught him what she knew about algebra, and so he could understand logarithms and things like that. So as a professor, having grad students of his own, he's watching them have the same struggle he did, taking weeks or months to do what we would consider very menial calculations now that we'd have done in a fraction of a second on a computer. And he was motivated to find a better way. So his first attempt with another professor that was taught statistics was to modify an IBM tabulator to analyze complex spectra. This worked. They wrote a paper on it, and they annoyed IBM in the process. He found out later, due to some litigation that happened decades from then, that IBM had put a note in the file that said, "Don't talk to John Atanasoff."
One other question, is that a computer there in the photo?
Yeah, this is an IBM tabulator, which is
No, the lady on the right, is she a computer? That's what computers used to be.
yes. I don't know. This was an IBM stock photo, so they're assuming it's who's ever using it. But no IBM tabulators were harmed in this research.
She have platform shoes?
So another type of computing device that Atanasoff worked on early was an idea of a student of his by the name of Hahnemann. And they called it the Laplaceometer because it was an analog machine for solving Laplace equations in 2 dimensions. They also wrote a paper on this, and I believe both of these I was able to find the scanned documents from the Iowa State University archives and put together a PDF rather than individual pages, and that is on your thumb drive. So everything I could collect on this, I put on thumb drive, and I can bring down the books that I reference in the bibliography later if you want to have a look at them.
Around the edges of the surface, and then you measured it.
So Atanasoff was actually the one that coined the term analog computer, being a device that represents it. The way it functions is an analog of the phenomenon you're trying to study, and it has a measurable physical parameter such as distance or current or pressure that you're taking your reading from. And because of this, the resolution is limited. And this is a quote from him here that they're generally limited to 3 or more base 10 places. And setting them up or trying to reconfigure them for other problems was quite difficult or perhaps impossible. And this was a list he made of some of the analog computing methods at that time. Now, digital computers he originally called computing machines proper. And this definition of digital computers is mine, so it's not really great, but it's a number represented by a discrete value, such as we would count with. It doesn't matter what the base is, but generally at this time, everybody thought in base 10. And most adding machines and the tabulators and things like that all operated base 10. And these are some examples of digital machines, even an abacus, because you have each beat represents a discrete value. The adding machines, the Monroe calculators, the tabulators. They were all complex mechanically, had very limited memory. The largest at that time was the big IBM tabulator, which had about 266 bits of memory. And one idea that he had was to gang together a tabulator and several Monroe calculators on a common axis. And, it was mechanically unfeasible. He could have done what he wanted, but it just wouldn't work. So between 1936 and 38, in his spare time, being a university professor, which isn't a lot, he thought about what could be done. What would the shape and functionality and method of operation of such a machine be? He could get by with just knowing how to add and subtract, because multiplication and division you can use as functions of addition and subtraction. What medium would the machine use? Would it be mechanical or electrical or some combination? Of course, the state of the art then was mechanical machines. And he actually did a series of calculations, which he wrote up in a paper, which is really interesting, to find the most efficient base for addition and subtraction and multiplication and division. He just didn't immediately think, well, it should all be in base 10 or it should all operate in base 2. And as I recall, he found that multiplication was more efficient in base 2 and division in base 4. But it didn't make any sense to have a machine that operated in 2 different bases. And again, the tabulator's memory, yes.
Number 4.2, was this written before the late 50s or early 60s?
1936 to 1938.
Oh, okay. But the word condensers, we haven't used that for.
Right. Yeah, so I'm using some of Atanasoff's own language here to kind of help convey his thought process. But I grew up with my dad and my grandpa saying condenser, so. And He's also thinking about storage at this time. Could it be electromechanical, flipping a spring-loaded lever of some type? There was Paulson's magnetic wire, which was a thing at this time, but he thought that would be overly complex for what he could get the money to do. Using tubes for storage might be possible, but you would need a lot of tubes and a big power supply, and it would be very expensive. He didn't have the money for that. And he also thought about condensers, if those could be made to work, or capacitors for, as we say now. So I like this picture of Atanasoff because at this time in his life he was very unhappy because he wasn't getting anywhere with this problem. He didn't know which direction to go. And this is a great story. So after supper he goes back to his office and he's thinking about this and he's getting very, very, very frustrated because he can't come to a resolution. And he decides just to get in his car and drive so he's not thinking about the problem. So he gets out on the highway and he's driving at a high rate of speed and realizes hours later that he's at the Illinois border. And he sees a roadhouse. And at that time, Iowa's dry. He couldn't get a drink in public in Iowa, so he pulled in, ordered a drink, sat down, relaxed, and then it came to him. And these are, his notes he made after that he would use electricity and electronics as the media for the computer. And in spite of custom, I would use base 10 numbers, binary, for my computer. And he learned about base 2 numbers from a book his mother had, which had a chapter labeled Mathematics in Bases Other Than 10. But he was never able to pin down what the title of that book was. He would use condensers for memory, but regenerate it to avoid lapses. And he called this at the time jogging. And he likened this to the mother sends a little boy to the market to buy some bread, eggs, and milk. And so the boy's repeating to himself all the way there, bread, eggs, and milk, bread, eggs, and milk. So he keeps regenerating that thought in his mind so he doesn't forget it. And he would compute by direct logical action, not by enumeration. And so he tried to limit the scope of what he was trying to do. He couldn't build a computer that would do everything, so he tried to think of a problem that he and his students faced, and that was solving partial differential equations. And he found out later this was actually one of the justifications for the British funding Babbage's machine, because if it could be made to help solve partial differential equations, that would be a big help because it took forever. One method you can use that is with a system of linear equations. Once you get enough equations and enough unknowns, it becomes a very difficult thing and very time-consuming and very error-prone thing to do. So 3 equations and 3 unknowns is not very difficult. When you get up to when he was thinking of 20 equations and 20 unknowns, that is a whole different ball of wax. So 1939 was the design and construction of this prototype unit, and this picture is from the later court case in the late 60s, early 70s. Based on a manuscript he wrote at the time after they completed the prototype. And he hired Clifford Berry. Oh, first, let me back up. He got a $650 grant from the Agriculture Department, and which was a good deal of money back then, but generally the university or the college at that time was not that interested in a computing machine. They didn't know what the heck a thing like that was. And he hired Cliff Berry, and they worked together to build this prototype, which proved his concepts. So this is basically a prototype ALU, if you would like. It had a carry and borrow storage mechanism, power supply, and on the disk in the middle is the radio capacitors, the memory, and there's a row of capacitors on each side. And it actually worked. So after this worked and they demonstrated it, he wrote this manual to try to get more money. Then in this period from 1940 to 42, he got a $5,300 grant from the Research Corporation of America. And when he got that much money at that time, this is, start of the war, into the Depression, which was a lot of money to get for a small college, for a strange project. And when he got this amount of money, the college took notice and thought, well, maybe this is something they should look into patenting. This is Clifford Berry standing beside it. the ABC computer. We'll see a big picture of that later. It was about the size of an office desk, but a little taller. It had 3,000 bits of regenerative capacitive memory, which was unheard of at that time. It was about 30 times faster than the largest IBM tabulator. The input was by standard IBM punch cards that were in base 10. The machine included a base conversion drum, so you'd feed in your cards in base 10 and it would convert it to base 2 and then store it on the drums. And the intermediate output, you would solve two equations. The output, or the solution of those two equations, was stored on base 2 cards, which were electrically punched, because he thought mechanical punched cards to save all 50 bits would be too complex and too expensive. And the final output was by dials, which were in base 10. So this is a drawing that was done for the court case that shows all the basic components of the machine. So each of the vacuum tube modules that did the addition and subtraction and reading and writing to the drums, they were all modular. And there was 30 of them, as I recall. There was a high voltage power supply and a bunch of thyrotrons to control the card writer and card reader. So in the front is the base 2 card writer, which used a high voltage on the order of like 3,000 or 4,000 volts to burn little tiny holes in card stock. And then the card reader used a lower voltage setting to read the holes. And you notice there's a motor here. This is a synchronous motor, and they have a common shaft and mechanism that runs the whole machine, and he described it as being mechanically clocked. And if you're familiar with some computers from the 50s that had drum storage. So pictures of the construction of the machine, angle iron frame, they're starting to fit components. This is a good picture of Clifford Berry operating the machine. And it worked when they got it done. The biggest problem was the card reader writer for the binary card reader writer. With extensive testing, they found there was a bit error every 10 to the 4th to 10 to the 5th bits. So for larger systems of equations, it wasn't adequate. They actually did find some card stock on campus that worked quite well. But nobody could remember where it came from. And having worked on a campus for the last 20-some years, I can tell you that's not that uncommon of a thing to find some material that works great in a project and not be able to track down and source the same stuff. So in 1941, when he's working on this, he goes to a conference and he meets John Mauchly of ENIAC fame. And they strike up a conversation, and Mauchly eventually comes to visit him in 1941, stays with him for about a week, goes and looks at the ABC, helps work on it, reads thoroughly the 35-page manual, asks for a copy, but there are only 3 copies existed, and the other 2 were out at various patent agencies and things like that. And so Atanasoff denied and said, you can't take it with you. So Mauchly asked for some paper so he could take notes. And later correspondence between the two, Mauchly even asked if he could build his own Atanasoff calculator, which that request was denied. And this is just one page of the manual. There's also a PDF of that on the drive. But things changed December 7th, 1941. The U.S. was now in the war. This is actually a picture of my dad's ship, the USS Latimer, toward the end of the war. I didn't think they came back to San Francisco that early, but anyhow. Atanasoff left for a job at the Naval Ordnance Laboratory. Clifford Berry graduated, got a job for a company that did work for the military. And that was the norm back then. There's a lot of staff changeover at Iowa State College. Nobody understood what the heck this computing machine was, right? If you're so far ahead of your time, nobody understands you. It's a big problem. And this is only remaining part, or one of the few remaining parts of the original Atanasoff Berry computer. In about 1947, a student who had worked on it some was ordered by the head of the physics department to tear it apart because they didn't need that piece of junk there taking up space in the basement of the physics department. But he kept this, and he actually had it in his office at Iowa State College. He went back there and taught. So they did find it. There's a prelude to this 1967 through 1973, that patent case, where IBM came to Atanasoff, who had just recently started his own business, and said, we want to sue Sperry Rand. We think we can break their patent. And Atanasoff said, well, I just moved into this house. I don't know where all my files are yet. I just sunk all the money I have in the world in this company, so did lots of my friends. And I don't have a lot of time to help you, but I can do what I can. And there was some type of deal then struck up between IBM and Sperry Rand for IBM to pay some small licensing fee. So the conjecture is that IBM came up with just enough information to keep Sperry Rand from wanting to litigate it.
Is this really an accurate comparison, or wasn't the IBM computer analog digital, and was the other one all digital, or how?
No, they both computed digitally. They both had mechanical parts as well. Just like modern computers up to very recently, well, you still have fans, but you have mechanical hard drives and mechanical floppy drives.
Is 5 to 1. I mean,
oh yeah, but it's not.
More memory on the ENIAC, or?
Yes, I believe it did have more memory, but it operated on similar principles that Mauchly learned from Atanasoff. But this was the patent case, was the principles that Mauchly and Eckert used to design and build the ENIAC, was that at least partially derived from Atanasoff. The case continued for, 5 years. There was tens of thousands of pages of documentation entered into evidence. One of the books that's in the bibliography, which I can bring down if you want to look at it, was written by a husband and wife team who were both on the ENIAC team. And very strongly took the position that, after reviewing all the court evidence, which he goes into extensively, that it was derived from Atanasoff's work. Atanasoff's feeling was later in life that there was enough credit to go around for everybody, that, Mauchly and Eckert did some amazing work, right? But he just wanted to say that, Berry and him did have a part in coming up with these ideas. So in 1994, a group related to Iowa State University decided that they would try to reconstruct the ABC using period materials, and got the money to do so. The original Atanasoff Berry computer cost about $6,000 to construct in the 1940 time period. The reconstruction in 1994 cost $300,000. So in comparison, in 1994 dollars, the original ABC would have cost $64,000 to build. So the reproduction was several times more expensive than the original. But they did prove that it worked. And it worked just like the manual that they wrote for it said, that type of thing. And I think the next slide, if I can make this work.
Hello, I'm John Gustafson, and this is Charles Schorb, and this is a replica of the first electronic digital computer, the Atanasoff Berry computer. The Atanasoff Berry computer, or ABC, was built at Iowa State between 1939 and 1942. This replica was completed in 1997. Using this replica, we will take you through a complete example of using the machine to solve a set of equations. Each of these vacuum tube assemblies does the arithmetic for one number. You can see 15 of them here, and there are 15 just behind them. The construction is modular, like it is in modern computers. The modules operate in parallel, so the ABC was not only the first electronic digital computer, but the first parallel computer as well. The ABC can hold two equations at once, one on each of these drums. The ABC was the first computer to use binary digits, or bits, to store numbers. The bits are arranged in columns on the memory drum. You can see 30 columns on this drum, and each column has 50 bits. So the entire storage of the computer is 3,000 bits. That's about a third of a kilobyte. To solve a full-blown set of 29 equations and 29 unknowns would take about 25 hours. So for purposes of this demonstration, we'll just solve 2 equations and 2 unknowns, the ones shown here. 2x plus 4y equals 8, x minus 3y equals minus 11. The first step is to enter the data into the ABC. There is no keyboard for data entry, so you have to punch the numbers in on cards. These punch cards are the same type that were used until the 1970s for getting data into a computer. Our first equation is 2x plus 4y equals 8, so we punch in the numbers 2, 4, and 8. You may have also noticed that we're using only whole numbers. The ABC did not use floating decimal points, so you scale up the numbers until everything is to the left of the decimal point. That took about a minute. While we're at it, we'll make the card for the second equation as well. For x minus 3y equals negative 11, we enter 1, minus 3, and minus 11. Notice that to make a number negative, we type a 0 for the first digit. If it's blank, it's assumed positive. Now we're ready to read in a card. We type the numbers in decimal notation, but the ABC works in binary. We convert the decimal numbers to the bits that the computer uses for calculations by use of the base 2 conversion drum. This is a different kind of memory drum. These pegs represent a table of binary numbers. When a peg touches a brush, it produces a binary 1. If there's no peg, it means a binary 0. Now we'll turn the ABC on and enter the data with the base 10 card reader. This meter should read plus 120 volts and minus 120 volts when everything is warmed up and working correctly. The machine draws less than 1,000 watts of power, less than your typical hairdryer. It plugs into any wall outlet. Now we'll turn the motor on that keeps the drums spinning. A power train keeps the memory spinning, just like the motor of a disk drive. It also produces a 1 cycle per second clock to synchronize everything. The motor is synchronous with the 60 cycles per second from the power outlet. The drums rotate once per second. The 50 pegs, one for each bit in the number, pass by brushes at the same rate as the 60 cycle per second line turn. That leaves 10 cycles blank, and you can see the blank part of the drum. This was the first dynamic memory. Inside the drum are 1,500 capacitors, one per peg. Capacitors store a voltage to represent a bit and get refreshed once per second so the charge on the capacitor doesn't fade away. The first thing we're going to do is make sure all the memory is clear. The operator console has a switch to clear the memory, and after one revolution, everything should be set to 0. The card reader is mechanical. The reader mechanism moves while the card sits still. Every time a brush passes over a hole, it makes contact with the brass dots under the card, and that completes a circuit. Each brass dot connects to a brush that reads the conversion drum. It's hard to see now that it's moving, but the pegs on this drum form a read-only memory. It's a table of binary numbers that correspond to every possible hole in the IBM punch card. So for the number 11, it reads the 1 in the tens column, looks up the number 10 in binary, and sees 1010. Now the ABC vacuum tube logic adds that bit pattern to what is already stored in the rotating drum. The card reader brushes read the digits and converted them and added them as well. Some things happen 30 at a time on the ABC, and some things happen 5 at a time. Since the ABC doesn't have a modern computer display, we've hooked up a digital oscilloscope that shows what's on the drums in binary. If you're not familiar with this kind of oscilloscope display, it represents numbers with on-off
But most
bits,
of us here can
this
do
being
this.
off and this being on. The number 8421 in binary, if the 8 and the 2 were on, that would mean the number 10. If all 4 bits were on like this, it would mean the number 15. The operator now tells the ABC to copy those 3 numbers to the other drum for safekeeping. He then clears the first drum to receive the next card. We'll now enter the top equation. We entered the bottom one first so we can use the top one to eliminate a variable in the bottom one, just like you do when you work this kind of problem by hand. But you can do it either way. Like many computers that came later, the ABC speed is limited by the time for input and output. Each decimal takes 1 second to read in, so it takes 15 seconds to read in all the numbers on a punch card. We can save some time by working with smaller numbers and starting the reader at the first non-zero digit. With the number loaded, we're ready to solve the equations. The ABC eliminates x from this pair of equations by subtracting the second equation twice to give 10y equals 30, or y equals 3. If you know how to read binary off an oscilloscope, you can see the 10 and the 30 there. Let's read the number out using the ABC. To read the number out, we reverse the conversion process used to put it in. Punch cards are used as masks to select which number we want to read. This masking card selects the second column, which should have a 10. The output is like the odometer on a car, except that the digit wheels are independent.
These are
Decimal
the
values in
output
the
wheels.
conversion drum are subtracted from the number in memory, and this solenoid kicks the wheel by 1 digit until the subtraction makes the number change sign. Then the same mechanism that pushed the card reader moves to the next column and starts adding numbers. It alternates between adding and subtracting, and that's why the dials are numbered in alternating directions. The number 30 should still be in the computer. A different mask lets us read that out. We reset the odometer mechanically. That completes forward reduction of the equations. If we had done that using a large number of variables, we'd be happy to do this last bit of math by hand. 10y equals 30 means y equals 3. Now we back solve using that value for y. Both equations were altered by the operation of the computer, so we need to put the first equation back in. We also put in a new card that has this value for y. Since we're now eliminating y, we have to change the jumper over to the second coefficient. The larger the numbers, the longer...
Okay, there's a couple minutes left to the video, but it's on the drive. These are the 3 books I talked about, and I borrowed the name from the top one there. It's a good mix of a biography and technical detail. The best by far in technical detail and about the court case is the one by Birks and Birks. And the one by Jane Smiley is a good biography and does a very good compare and contrast to other computers of the day and other people known for coming up with computing ideas at the time. So they all 3 have different emphasis, but I would recommend all 3 books.
These books compare, sort of like comparing apples and oranges and grapefruit, because each one's doing things a little differently, and or speeds with speed parameter for evaluating and all of that.
Yes, but you're right. Things were very disjointed, right? Zeusa had no idea what anybody else in the rest of the world was doing. And Atanasoff tried to read all the available literature at the time when he started. Other machines.
If you look at the drum turning and you say, I got 1 drum of the drum turn in terms of today's.
Yeah, but it was still 30 times faster than the fastest IBM tabulator at the time.
Still, 29 equations, 29 that's an incredible problem.
Yeah. And what really impressed me about Atanasoff's method is he had very limited means, very limited money to do what he was doing, and he found a problem that he could prove his concepts with that would still be useful. And, in contrast, his project was about $6,000 total. ENIAC was about $500,000. And a similar difference in the number of people working on the project.
It was, in its own time, revolutionary right now.
Right. So, set up something very interesting. Yeah.
Okay, so digital computing went directly from the mechanical, the Frieden type mechanical clunkers to this electronic And I've always wondered why there was no intermediate stage electromechanical using relay logic.
Oh, there was. Zusa.
Was there?
Yeah, Zusa did that. The Harvard Mark I was electromechanical. I think the Japanese made relay-based calculators until the 50s.
Because, I mean, if you have, with this technology you showed us, suppose to store 1 bit of information, suppose it takes 1 watt of power. Okay, 3,000 bits, that's 3 kilowatts.
No, that whole machine was about 1 kilowatt.
Uh-huh. But, I mean, that's big power. But with an electromechanical relay, you flip it and a permanent magnet holds it there and it stays forever with no power. So the power advantage of going with electromagnetic relays is significant.
Yep, then you also have, other mechanical considerations, speed and
Of course, it's
longevity.
slower,
Yeah. Yep. Okay, any other questions? Yeah.
You said this realization occurred when you crossed from Iowa into Illinois. Is it documented what town it was in?
Yes.
Was it Quincy?
Rockville?
Quincy, Illinois? No, Rockford, Illinois.
Rockford. It was something like that. Rockford, Rockville. Yeah, it's well documented. And that was the thing with the court case, that Atanasoff had all his correspondence with Mauchly, correspondence with suppliers asking about components, all the drawings, things like that, the things he had done before, testimony from students that had worked on the machine. And Mauchly really had an analog computer he made that was described in the literature at the time, and the only digital thing that he had made prior to visiting Atanasoff was a relaxation oscillator with neon bulbs, which he described as a binary counter that could count to 1.
All set? Well, thank you very much.